Hello, everyone, and welcome to EE Engineering Training Days. I'm Amy Kalnoskis, the editor of EE World Online, and welcome back to those of you who have been steadily watching us twice a month so far this year. And for those who haven't, these are our tutorial educational training programs that we have twice a month. Today's is on highly efficient power conversion in clean energy applications, and this is sponsored by Allegro Microsystems. So before we go any further, let's just get some housekeeping items taken care of. So the PowerPoint and any additional resources can be downloaded in the resource widget, so check that out. I also want to note that our speaker today has also listed within the PowerPoint several pages of resources, or a page of resources that link to pages online that you can check out as well. You can ask questions at any time during the presentation. We don't have to wait until the end. We're just waiting to the end to answer them. And if you're watching this on demand, also don't be shy. You can still ask your questions and we will make sure that they get answered. Speaking of on demand, you can find these and the other EE training days at eetrainingdays.com. One other thing I want to note as you're watching the PowerPoint, stick around to the end for lots of reasons, but one of them is we've got a survey for you to fill out, so a little interactivity here. Again, this is sponsored by Allegro Microsystems, so thanks very much, Allegro, for participating kind of frequently in our EE training days. So before I go any further, I just want to introduce our presenter, and then it's all him, not me. Emil Pavlov is the Strategic Marketing Manager at Allegro Microsystems. He focuses on clean energy systems and designing towards a more sustainable future. His work is geared towards solar power, electric vehicle charging infrastructure, energy storage systems, and heat pump applications. Emil has both a BS in science and an MS in science degree in physics from Heidelberg University in Germany. So with that, I will pass it on to Emil.
Thank you very much, and welcome to everybody who's either tuning in live or listening to this on demand. Let's just briefly go over what we will talk today before going into the topic itself. Start with a short introduction, then we'll go over some of the advantages of GaN semiconductors for energy conversion. Then we'll talk about a very important part of using FETs, which is the drivers. We'll discuss shortly how it is, what's the importance of current sensors with power conversion systems, and then we'll go over some concluding remarks. So first thing first, before we start the conversation, let's align on what we understand when we mean clean energy, because I've noticed this may vary sometimes from company to company or region to region. In any case, today we'll be talking in the context of the following 4 applications. These are solar inverters, EV charging infrastructure, heat pumps, and energy storage applications. And this is probably a pretty bad way to start a presentation, especially if you've been also experiencing very wild weather in April, like we have been having here in Central Europe. So on the left, you can see the CO2 concentration in the atmosphere since we started measuring that directly. And on the right, you see the global annual temperature since we have record keeping. And I think those 2 graphs very clearly show that we are not on a sustainable path towards our future. However, even though it may seem a bit bleak, I don't think we should be very or only pessimistic about it. There are a few things that we can do about it, and we'll actually cover these topics in the webinar today. So if we look at how the energy source has changed through the years, on the graph on the top left, you can see first the energy demand has been steadily rising, and since the middle of the last century, it has started changing the slope, and there is no sign of slowing down. But you can also see some shift to newer and emerging technologies like solar and wind power. And on the bottom left, you can see how our energy production, how much CO2 does it cost us to produce each kilowatt hour. And there are three lines showing what we're currently on. This would be the blue line, the yellow would be what we have announced that we will do in the near future, and then the gray line would be what needs to be done in order to meet our ambitious goal of having zero net emissions by 2050. So it is obvious that there is some way to go, but I think it also very clearly outlines that there is not only need to switch to more renewable technologies, but to make them more efficient in the sense that we have a lower carbon footprint with all the energy that they produce. And we may not be able to directly influence the politics, like what the yellow line or what the blue line are, but I think we in the engineering community have a unique possibility to influence the technology that I think shifts quite a lot of how energy is produced. So if you look at the share of solar power that has been produced in the recent years, it's not like there has been more sun that has been hitting the earth, but we have been able to create more efficient and more cost-effective technologies based on constant innovation in this space. And I think if we are to meet our goals, we can see that it's definitely, we need to continue that path of innovation. So one of the next steps towards that innovation path would be exploring new materials or emerging materials. This would be wide bandgap semiconductors. And here I have a short summary table to compare how do they differ from typical silicon, which is the most commonly used material for power electronics. And you kind of can see from just, even by squinting it, you can see from the color coding that the majority of the advantages are lying on the left side of the table, which is the new generation materials, rather than on the right side. And we'll go in a bit more details what these individuals properties mean. I would just maybe shortly summarize that usually silicon carbide finds a lot of application where you are looking for very high voltage or very high power because of its higher isolation working voltage and its higher thermal conductivity compared to GaN. Although this can be also sometimes solved with a little bit of system design choices, and it's not always a clear-cut solution. But if we look at the other properties, it's very clear to see that GaN has a lot of advantages when it comes to efficiency due to the much lower losses and the better performance. So let's look at a bit more details in some of the properties. One important property of transistors is the RDS on. And here on the graph on the left, you can see that plotted on the x-axis. On the y-axis, there is the gate charge. And bear in mind that this is a logarithmic plot. So a bit of an easy way to improve the RDS on is to make the gate a bit bigger, meaning that you have less resistance. So this is not just improving the performance of the material or the technology by any means, it's just a specific design choice. So it's always very important when you're looking at RDS on to look at what gate charge are we talking about, because just tuning that can change it without making any significant changes to the properties. So you can see the silicon here is plotted in gray circles, silicon carbide in yellow circles, and GaN in blue triangles. And you can see the different clouds of scatter points lie at sort of a threshold or limit line, which is basically determined of how good can we achieve that switching, that conduction property. And I think it's also very easy to see that silicon lies above a silicon carbide, and GaN has a significant advantage compared to those both materials. But just the conduction property is not all the story when we're talking about transistors. We mentioned gate capacitance, and capacitance is something that has a direct effect on how fast can you switch on and off your transistor. So here on the left, you can see graph comparing the switching losses of different transistors. This was a study based on all available transistors in the market, or at least a very large portion of that. And when you are looking at lower frequencies, it seems that silicon maybe, or silicon carbide may be a bit more preferred choice due to cost and relative performance improvement. But once you go to a bit higher frequencies, it becomes more and more a clear case in favor of GaN when you're looking at switching loss and cost effectiveness for the performance. And one thing is to note that was also noted in the table before is that a big difference with GaN FETs is that they don't have reverse recovery losses. This means first they're more efficient, but also you don't have the recovery time that you need to wait before you're able to switch again. And this plays a major role once you go to higher frequencies. So maybe an obvious question would be, why do you even want to care? Why would you even care about higher frequencies? So there are several reasons for that. First, you can reduce the size of your passive components. So for example, here on the left, you can see plotted the volume of a switching transformer based on the operating frequency. And you can see that it, as expected, becomes smaller and smaller. Also, you can have smaller inductance of your coils when you go to higher frequencies, because you can achieve the similar reactance of your overall system. This also has some benefits with regards to size, but it also can lead to a bit lower stray resistance, which has additional benefits. It can also make the whole system a bit more compact, a bit more cheaper. It can give you better performance, and it can reduce voltage transients when you have lower inductance. And in this table, you can see what kind of power conversion systems come for different applications in clean energy, specifically the one that I listed in the beginning. A very common system you will see is isolated DC-DC conversion. This could have very different parameters or purposes depending on what exactly you have or you need the system to perform, but it usually it's used to change from different voltage levels depending on what you need. You can also have power factor correction systems which is necessary when you want to use high power AC current, or you want to have something that needs DC current that is feeding in from the grid. You can also have some DC to AC inversion. This could be either from your solar generated power, or it could be for your compressor in a heat pump. And sometimes you can also have AC to DC bidirectional AC to DC conversion if you want to have some batteries that has to be charged from the grid, but you also want to feed power back to the grid. And based on those applications and the properties that we discussed for the transistors, we can have a look at approximate mapping of which technology could find application in which technology can be applied in which application. So as you can see here on the bottom axis is the frequency, and on the left axis is the power. As discussed, once we start going to higher frequencies, GaN becomes to be more and more advantageous. Once we go to the highest powers, silicon carbide with its higher voltage and higher thermal conductivity becomes to be more dominant. But there is definitely some overlap, and there is also overlap with a bit more traditional material like silicon. And sometimes what is the best for each specific application may depend on the specific driving factors for each application, but usually better performance, higher efficiency, and sometimes better cost effectiveness can come with GaN, or in some cases with silicon, despite the individual components being a bit higher in price than more traditional silicon. So with that being said, let's look at a bit of a specific example, in this case, a power factor correction system. And here is compared what is the system loss for using superjunction FET, silicon carbide FET, and GaN FET. And you can see that there is a very good advantage when you go to GaN, and this can have very noticeable effects when you scale it out to a lot more systems that are being mass produced, and just what might seem as a small difference could have a very significant impact, as we mentioned, on that carbon footprint on the energy that we produce. And one other thing to note is that not only your switching performance is improved with GaN, which also improves the system performance, but as mentioned before, when going to higher frequencies, you can actually save up on other components, and in the end, you might end up with more cost-optimized system when you compare the whole design, not only the individual transistors. So why are isolated GaN GaN FET drivers needed? So the drivers can have equally important role as the transistor itself. I know usually people choose their FET and then worry about the driver, but you like to have a driver that is able to perform equally good as your transistor. You don't want that to be your bottleneck. And specifically when we're talking about this application that we mentioned, we are very often working with high voltage that needs to be sufficiently well isolated from your control side and your power side. As I said, you want to be able to keep up with your FET, so you need to have significant power throughput, and you need this to be efficient, because if you're switching quite often, you'll be paying every time this loss, every time you perform switching on your transistor. When you go to higher frequencies, you want the driver to be able to control with precision and stability your power scheme. Otherwise, it will be just, you will be getting more disadvantages than advantages of your system. And last but not least, you want that driver to have high robustness against transients that can come with high switching, and it has to be robust against noise, and it shouldn't be feeding back to your control system. So why is isolation needed? I briefly touched on this before, but I just want to go over it in a dedicated slide. So there are three main reasons. First is safety, meaning you want the end users to be protected from the high voltage, and you want that there is no chance of people accidentally electroshocking themselves just because they touched currently exposed or currently live part of the system. Then we want to have protection of the microcontroller or the control electronics, which can be very sensitive and may not be so robust to the high switching powers that we have on the high voltage side. And as mentioned before, we would like to limit interference, which can come from ground loops or with some noise feedback that would be coming if we didn't have a galvanic isolations between the control side and the high voltage side. So what are three classical ways to achieve data isolation on your gate drivers? So it is easy to isolate to achieve the galvanic isolation. The problem comes when you want to send signals through that isolation, specifically when you need to send power for the gate driving, meaning you want to be able to control the charging and discharging of the gate of the FET, but this has to be controlled from the isolated side. So that means you need to be able to transfer that gate charging power via some way through your isolation barrier. And there are three approaches to this. You can use an isolated DC-DC converter module. You can get auxiliary winding on your main transformer, or you can use a bootstrap circuit. And all of those systems have their own advantages and disadvantages, and sometimes designer will go from one or the other depending on what program they value more and what has higher priority for their system. I'll just briefly explain the different technologies. So for the DC-DC converters, they tend to be off the shelf, and you can just plug them in your design. But unfortunately, they are also very bulky and can be sometimes a bit tricky to integrate. They also come with the respective price tag, so they may not always give you the simplicity that you require. The auxiliary winding on the transformer can kind of solve that because you automatically get the isolation through the transformer, but this moves the problem from the DC-DC module to the transformer, and now you have to make sure that your transformer has the space and the design to be able to integrate that winding. And then maybe the least complex one would be the bootstrap, in the sense that it doesn't require too much mechanical space or changes to your system, and it can be relatively cheap to implement compared to the other ones. But it also has its limitations, mainly in performance, and it can become very complex if you want to use gate drivers that have to go to negative voltages in order to ensure that your transistor has completely switched off. So as everything in a design process, there is no ideal solution. But I do want to present something that I believe solves a majority of those concerns, and this is the power-through technology, which is briefly shown in this slide. So this is an Allegro proprietary technology where it is able to integrate the isolation barrier of the gate driver with the supply in a single package, which has a very typical dimensions of integrated circuit and not the bulkiness of any of the other systems that I mentioned before. And this has the advantage that you get rid of all the extra components that you would otherwise need to worry about, and this gets integrated in a nice solid package. And this brings quite a lot of advantages with itself. So because everything is so integrated and designed with everything from the beginning in mind of optimization, and everything is adapted to deliver as much power as it needs, but not more, it means that you have a very efficient system. You get rid of all the components, so you can save some space, some design effort, and of course, this also saves you some costs related to your benefit, related to your BOM. And one thing to note is usually you wouldn't have just a single transistor in your system, but very often you would have multiple, and depending on the specific topology, on the specific purpose of the power conversion, this can be anywhere from 3 to 10, 15, 20, depending on what exactly you need to perform. And you can imagine the complexity of providing isolated power scales with the number of transistors or gate drivers that you have in your system. And here is a slide showing how that translates to specific topology of that power distribution. So if you can have several different versions. You can have the centralized, semi-distributed, or distributed system, and each of them have their own way of solving that power distribution in a system with a lot of elements. But out there to say that nothing beats the simplicity and the effortless and the efficiency of the integrated solution that I just mentioned, because it does solve a lot of those issues in an inherent way without having to spend anything extra for that. And here's a bit more detailed look in how does that translate to a specific system. I won't go to each element or each element of that block diagram. I'll just bring your attention to the color legend that you have on the top and on the bottom. You can see all these colors on the top side, which represent different voltages and voltage supplies that you need to bring to your gate drivers, and how much this is simplified when you use the power-through technology, because it has its integrated voltage delivery system with isolation. So you only need to supply the primary side, and the secondary side is already integrated into that. And everything is just one single color. And if you're wondering, this is an example for electrical vehicle charging infrastructure, when you have AC conversion to battery voltage conversion. And another hidden property that usually comes with isolated gate drivers is the input-output common mode capacitance. And you might be wondering, well, why is that even important? I've never even heard about it. And yeah, that would be understandable, because the majority of the previous implementations that I mentioned for isolated power supply, most of them have very similar values or performance in that regard. And usually it's not so much anything that you can change anyway, so it's not something that you need to worry. But why is it important? It's because it creates a loop, a capacitive loop for your signal to back couple, and this can have quite a few negative impacts on the performance of your system. And another inherent advantage of the power-through technology is because everything is so integrated, that capacitance is just much smaller, because everything is much closer to where it needs to be, and you don't have unavoidable stray capacitance. So if you see on the bar plot on the top, there is just a comparison of very common isolated gate drivers for GaN FETs, and the pass-through has only 2.2 picofarads compared to the next one, which would be 17, or the typical one, which is well above 30. And what that can translate for the system performance is quite a few advantages. So you are no longer charging unnecessary high capacitance every time you want to switch on and off your transistors. So this gives you better efficiency or less power loss. It also increases your power density. It simplifies the design when you're using this integrated system. And another thing important is when you have lower capacitance, that means you have lower requirements for your passives further down the line, or you also, or other way to look at it, you have a significantly lower noise with the same passive components. And of course, one thing that is should not be overlooked is the integration of that power delivery system, of course, means that you need way less external components to achieve the same or even better performance. So up until now, the conversation was mainly focused on the switching side of the power system, but equally important is the current sensing side for several reasons. One of them is it can provide safety. So if you're having some short circuit, or you want you see that the system is behaving in a unpredictable way, or it's going through some runaway process, it's important to be able to sense this very fast, very reliably, and robustly in order to take corrective actions, or to even to shut down the system before things get into a very hazardous situation. Another thing is when you want to optimize the power delivery, especially when you're talking in the context of solar inverters, it's necessary to be able to monitor both the voltage and the current in order to optimize your performance. And last but not least, for a lot of power conversion topologies or systems, it's usually necessary to be able to monitor the current that is flowing through the system at specific points in order to optimize it, or even to be able to control it, or to make sure that you are within regulation requirements. So there are a lot of places where you can insert a current sensor, but it can be mainly grouped in three categories: high side, in phase, and low side. And this is related to where you are positioning the current sensor in regard with the transistor. So if it's next to your ground, this would be the low side. Next to your high voltage, this will be your high side. And if you have it on the path where the current is flowing either in or out, this would be in your in-phase system. So in this case, for this half bridge, this would be just next to the inductor. And all of these positions have their different performance advantages or drawbacks. Usually the in-phase gives the most design freedom to the system engineers. It has the most robustness, and it gives you the most monitoring ability, but it also has probably the most challenging or demanding requirements for its implementation. And specifically when we're talking about GaN FETs, as we mentioned, when we're going to higher frequencies, this means that your current sensing capabilities need to be able to match those, and actually you would like to be able to exceed them based on the Nyquist theorem. So if you're looking at 1 megahertz of switching, you'll be easily looking at least double that for your measuring capabilities. You also want your measurements not to be your bottleneck in the power conversion, so it has to be able to handle that kind of power throughput. Of course, you also like to minimize the disturbances, minimize any potential losses, and as mentioned before, you still want to be able to fulfill all the requirements with regards to safety, conformance, accuracy, and last but not least, you want your measurement to be as least disturbance to your system. So you want something that is able to be compact in size in order to be able to be integrated easily to your system. So what are the different methods to measure current in power conversion systems? They're roughly illustrated in this slide. They're mainly, I would say, 6. Some of them are related, so I'll try to group them and just talk about their similarities and their differences. So on the top left, we can see approaches using shunts. This would be a sensing resistor that is inserted through your line of where you want to measure the current. And basically, by measuring the voltage drop across that resistor, you can calculate the current through Ohm's law. That is relatively straightforward. The problem comes when you want that to be with isolation. And there are two main ways to achieve it. One is sigma delta modulator, and the other is isolated shunt amplifier. They more or less achieve the same purpose in a bit different ways. Then on the right side, on the far right, top and bottom, you'll see current transformer and Rogowski coil. They have very different diagrams here, but they function on a very similar principle. You have some kind of an inductor that is placed close to your current carrying line. And when you have alternating current flowing, there is current that is being induced in your sensing inductor. And that way you can sense what is happening in the line that you want to sense. For the current transformer, this is, as the name says, just a transformer that is being put on your measurement line, and then you apply some electronic circuits in order to be able to get voltage out of that, and the isolation comes from the transformer itself. The Rogowski coil is different from the transformer in the sense that it only has usually one coil around your current carrying wire. So you just only have basically the secondary side of the transformer. Another difference is that it doesn't have any ferrite material as a core. It is just air core. But other than that, it also works on the same induction principle. And a big distinction is that it only works for AC because you are not able to induce any current with with DC. The shunt amplifier, the shunt sensing works with both AC and DC, but it can suffer from either very high power loss due to the heat generated in the sense resistor, or very poor resolution if you choose a smaller resistor, because this gives you, and it puts you in a situation where you need to compromise with one of the two. A sort of a middle way between the two would be magnetic sensing, which can be implemented either with Hall and TMR. And there you have your current carrying conductor that produces magnetic current by itself, and by having a sensor, you can detect that magnetic current and calculate what is the current causing that magnetic field, and that works for both AC and DC. And here again, you can see a table summarizing the main characteristics for each sensing methodology. I won't go in details for each one of them. I briefly touched on some of them work only for DC, some of them only work for AC, the others work for AC and DC. Very often the size would be a huge concern when you're talking about transformers or coils, or when you're looking into resistors. I briefly touched on the power loss that you can have, or the necessity of external complex or sometimes costly components for you to be able to achieve that isolation that usually comes inherent with the other methodologies. And there are always some drawbacks that come with each technology, but I would just, again, using the squinting method, say that the more you go on the right, the more greener fields or yellowish fields you have. And usually it's a place where you want to be generally navigating. And with that, I just want to briefly highlight a product that I'm very excited about because it actually brings you the best of both worlds. So it's a current sensor from Allegro that has both a magnetic sensor, a Hall sensor in this case, and an integrated inductor. So it has a coil and it's able to use the advantages of both sensing technologies and combine them in a single, very small and compact IC package without compromising anything. So it takes quite a lot of that dreadness of having to make the right choice because it already gives you what you're looking from both worlds. And with that, we're nearing our discussion time. So I just want to briefly go over some concluding remarks, and we can jump into the questions. I hope I was able to show you what advantages you can utilize when you switch to a next generation switching technology, what you need to consider when you're using wideband gap FETs, specifically GaNs, about driving them, about sensing them. And I'm really looking forward to the years to come to see what kind of innovation is coming in the areas of power conversion for clean energy.
Well, thank you very much, Emil. So we do have some questions here before we finish up at the top of the hour. I want to remind the audience that you can ask questions on demand. So if you had to book out early for any reason, or you are watching this on demand, go ahead and ask your questions and we'll make sure that they get answered. Also, I want to remind you that there will be a survey. So you should take an opportunity to answer those questions yourself. All right, so you did mention, Emil, that you had that chart up about the different sensors, and the greener it got, the better. Can you elaborate a little bit more? Zach has asked, does Hall or TMR have any specific advantages in systems using SiC or GaN?
Yeah, so that's a great question. There are different technologies that have a bit different properties. Generally, TMR would be a bit more sensitive, which would give you a better resolution when compared to Hall. It can be a bit more power efficient when compared to Hall, not only due to the sensitivity, but also due to the principle of operation. Also, generally, TMR would have higher bandwidth when you compare it just head-to-head with Hall. So you would usually get faster responses with TMR when everything is more or less kept to be the same from both. So usually TMR could give you the better performance. In the case of the 37030, that higher bandwidth doesn't come from the Hall, but comes from the coil. So that is, in a way, compensates the Hall having the lower bandwidth than the TMR.
Okay, great. Hopefully, Zach, that answered your question, but feel free to follow up. All right, so we know we're in a very cost-sensitive market. So the upfront costs of GaN devices are currently higher than those of silicon. What factors would I need to consider to justify the higher initial investment, in your opinion?
Yeah, and this is actually the major concern that we see on the market with the adoptance of GaN. Well, that and also them being a relatively newcomer, even compared to SiC. So one great advantage of GaN compared to SiC is that it's manufactured on standard silicon wafers.
Right.
So it has already a benefit of that established technology and that cost efficiency. And since GaN is a relative newcomer, it is yet to benefit from its economy of scale, whereas silicon and silicon carbide even would struggle to gain further cost efficiency there. Also, I mentioned this when I was talking about it's a bit blindsiding when you just compare the pure cost of a transistor itself. It's true that silicon would generally be the cheapest. Maybe silicon carbide might be comparable in some cases to GaN. Sometimes one can be cheaper or the other, depending on the specific parameters. But you also need to consider what comes with the better performance. We talked about increasing the frequency, which has quite a lot of positive impacts on the other components around. We talked about integrating more efficient power supply, which further increases your efficiency, reduces the extra components. You get better performance, so you don't need to spend as much optimizing, which means you have lower design time, which is another cost saving. You have smaller solution sizes in general, just based on all the factors, which can be another cost saving. And when you start to compound all these effects, you end in a situation where even if you had the same performance on the switching technologies, everything else that you can shave off from your system starts to add up.
Yeah.
And as we saw in the direct comparison of the silicon, SiC, and GaN transistors that I referenced in the beginning, when you look at the same performance, usually you would be much better for your money with GaN rather than SiC or silicon, because just GaN has much better technology characteristics. So in order to achieve that with other materials, you need to pay a premium for that extra performance.
Yeah, that makes sense. In other words, looking at the price, considering the cost of the GaN device itself on its own, just as it doesn't make sense. You have to look at it holistically for the entire system. Yeah. Okay. Thank you for elaborating upon that. I think we have time for maybe one more question. But remember, audience, you can ask on demand as well. So what are some of the ways to manage the thermal challenges associated with the higher power densities and switching frequencies by GaN FETs?
Yeah. So the lower losses definitely lead to a lower generated to a lower heat generation.
Yeah.
So this is one thing. With the same performance or power output, you have less to worry about that. Generally, your system could be smaller, or an alternative to that would be just to have a bit more spacing than your components, because you are so much more efficient with your like components, which means it allows for better heat solutions, as if you were having the bulky elements. And this is also one thing that usually also a lot of research has been done on, just comparing not only the switching performance, but the thermal performance of specifically silicon compared to GaN, because they have very similar thermal characteristics. And as I mentioned, GaN is deposited on silicon anyway. And I didn't show any results in the webinar because I didn't want to distract too much of the topic, but generally the result is very conclusive that you have just better performance, better thermal performance with GaN compared to silicon.
Okay, great. I'm going to try to slip in one last question. How critical can be PWM resolution for GaN HEMT drive on high switching frequencies of greater than or equal to 5 megahertz? If you'd like, I can repeat that.
Yeah, no.
Okay.
So when you go to these higher switching frequencies, you need to be able to control your system very precisely. So if you are not switching your transistors at the right time, you might even cause a catastrophic damage to your system. You can cause some fire. So you definitely want to avoid this, not only for just the loss of efficiency, but just for safety. And usually you would, again, if you follow just the Nyquist theorem, you would want your resolution to be double of your signal that you want to process. So you want to have 10 megahertz capability when you're switching with 5 megahertz. In practice, very often you also would like to have a bit margin on that. So for that means you have a factor that is more closely to 5, at least 3 to 5 than your typical switching time. So I don't want to do my math live on air, but you can just calculate what that means in terms of nanoseconds.
Okay, terrific. Well, thank you very much. I think that's going to wrap it up for us today. We're almost at the top of the hour. I want to thank you very much for that presentation, and audience, thanks for hanging in with us. And again, feel free to ask your questions. I want to thank Allegro Microsystems for sponsoring this EE Training Days, and Emil Pavlov, thank you for the presentation itself. So all of you have a great day. Emil, thank you.
Thank you, Zoe.